All right. Hello, everyone. Good afternoon. Um, let's see. So same old, same old. Remember, your all's quiz 2 is due not this Saturday, but the 29th. Things weren't showing up on the to-do list for some reason, but I think I fixed that. There was no reason why they weren't, but hopefully now they are. I tried to test it, so hopefully that helps keep track of things if that wasn't working before. As long as an assignment has a due date, it should show up on the to-do list, which helps keep track of things. But I had a couple students notify me things weren't. I just opened the quizzes and then closed them. And I don't know. I didn't really change anything, but it seems to work now, so that's good. To that end, great. That's there. I guess the other thing to note is our first test is in 3 weeks. That's still a lot of time. We've only been meeting. This is the third week. 1, 2, and then 3 weeks we'll have the test. So I guess we're halfway to the first test or something. The first test, remember, it's basically kinematics and forces. So we're going to finish up kinematics today, and the next 2 weeks we'll do forces. And then we'll do a review on Tuesday, and then we'll have the test. So anyway, good ways out. As it gets closer, I'll give you all more details and things like that. But lots of time, but yeah, as long as you stay on top of things, it's fine. 2D motion. So we kind of just had a little bit of time at the end of class. We did the 1D motion. We talked about gravity. Gravity makes everything have an acceleration of negative 9.8 in the vertical direction, in the y direction. That's going to be really important today. We're going to use that a bunch. Remember that things have a velocity of 0 at the highest point. If I toss something upwards with 10 meters per second, it comes back down. It'll hit my hand with negative 10 meters per second. All that good stuff. That's where we kind of spent a good amount of time last time. And then I mentioned this to you all for 2D motion. 2D kinematics is just 1D kinematics. We're doing it twice. X and Y are separate. That's going to be the name of the game today. That's what we're going to be spending all the, today we're just going to be chatting about things, doing some example problems. This entire section doesn't really have anything new. It's just taking vectors and it's taking 1D kinematics, taking it all together, and you get 2D kinematics. X and Y are separate is really the only skill that we need to build on alongside doing everything together. So rule of thumb with these problems, you're going to start with a problem, write down all your givens. You're going to split everything into X and Y. So for example, if I give you all, this is going to come into play today later on, if I say I kick a ball at an angle of 30 degrees with a velocity of 10 meters per second, you're going to have to make a right triangle. You're going to have to split into X and Y to solve the problem. Splitting into X and Y means draw a triangle, find the component of the velocity. That we're going to do this today, so don't feel like. But we're going to have to split everything up into X and Y. Do all the kinematics. We're going to find time, either in the X or in the Y, and then we'll use that to find whatever we want. That's going to be the name of the game. And then maybe at the end we'll recombine X and Y. The only way you're allowed to recombine X and Y is Pythagorean's theorem. If you have two sides of a triangle, that's the only way. It's the only way to combine things that are perpendicular. So anywho, I skipped a bunch of slides. I'm not going to really spend much time on them because I think they really don't add too much. They're just kind of the definitions and saying it's. So like this one, it's displacement. But instead of just being one dimension, now it's got two of them. Most of these slides are just saying that. We will practice some of these skills real quick. So we will spend, this is vectors. So I've got a triangle here where I give you the displacement. And given, there's no numbers here, but I'd say, hey, here, delta R, how would you find the X component? That's the question. How would you do it? Would you take the delta R and multiply by cosine theta? Would you take the delta R and multiply by sine of theta? Would you take the delta R divided by cosine theta? Take the delta R divided by sine of theta? What math would you do? So this is just practicing vectors, making certain we're remembering this, how to do this. So try it out. Remember, there's only one right answer here. Every single one of these options is different. Only one is right. So check with the people next to you. If someone has a different answer. Same old, same old. Don't forget SOHCAHTOA. SOHCAHTOA. If that's not being used, you're probably not doing it right. All right, we'll spend like 20 more seconds on this. All right, 10 more seconds. 5, 4, 3, 2, 1. Speaking of Top Hat, I did sync all the grades over. As long as you're showing up in Top Hat, you're good. There is some people that aren't syncing over, and I'm not sure why. As long as your grades are showing up in Top Hat, that's really the most important thing. I'm working with Top Hat to figure out why some aren't syncing, but worst comes to worst, I can manually type those over if I need to. As long as they're in Top Hat, you're good. If they're not, it's not good. All right. So, SOHCAHTOA. SOHCAHTOA. So we can label our sides. This is the hypotenuse. One of the classic challenges when it comes to this is determining which side's the opposite and which side's the adjacent. Once you know how to do this, it's really straightforward. You just say, hey, here's my angle. Which side is opposite that angle? Oh, it's this. That side's the opposite. Oh, what side's next to my angle? That's my adjacent. It's always with reference to the angle. So then we say, which one are we solving for? We're solving for the opposite. So we need to choose which of these has the opposite, and it's all in terms of the hypotenuse. So the only one with the opposite in the hypotenuse is sine. So sine of theta is opposite over hypotenuse. So sine of theta is delta x over delta r. Rearrange things, move the delta r to the other side, and it's sine. One of the habits that people fall into, because it's pretty common for this to be true, but it's not always true. Habit people fall into is that x is always cosine. That's not true. When you're solving for the x component, it's often cosine, but not always. So you should always go through this process. You should always go through, am I solving for the opposite or the adjacent? You cannot do not fall into the pattern of, oh, x is always cosine, because I just gave you an example that's not that case. So it's all based on the picture. You've got to draw the picture. You have to draw the angles. You have to say which one's the opposite adjacent. If you try to take shortcuts, that's where mistakes happen. Think through the logic. So it doesn't take that long to think through the logic, but if you skip it, you have a chance of making a mistake. So, okay, this is just a recap from last time, so I'm not going to bother with that. That's just remember the time to the top is the same as the time to the bottom. Remember, if I go up with 10, I'm going to put the answers here. These are the same questions from last time, but I'll just mark these in case you happen to reference this later on. Okay, again, just checking, can we do our vector stuff? So a bird flies 3 meters east and 4 meters north. What is the bird's net displacement? Try this one out, and then it's going to segue into the next one as well. You're going to draw a nice triangle of it. Is the answer 7 meters, 1 meter, -1 meter, or 5 meter? We'll only spend like a minute on this or so, minute and a half. All right, maybe like 20 more seconds. All right, and 5, 4, 3, 2, 1. Ba-doop. All right, so we're going to draw a pretty triangle. 3 meters east, and then we do 4 meters north. Remember, when you're drawing these triangles, draw one and then draw the other where the first one finished. So this is 3, this is 4. The result is a triangle. We're combining X and Y. And this is a really nice triangle. A 3, 4, 5 triangle is like the best. So it's just, again, do you remember how to combine X and Y? Just vector. There's like nothing fancy here. Just there's Pythagorean's theorem, which at some point was fancy, but hopefully now is commonplace. So this slide is nothing too crazy as well. This is the same old, this is just saying, hey, velocity average, now instead of just being delta x over t, it's all the displacement over t, all of it together. If you want the average velocity, get your x's and y's together and divide it by the time. But you can also write it in terms of its components. We will do that. These ones shouldn't have triangles on them, but so, and again, nothing crazy, nothing, it's just velocity, but hey, now it's got multiple dimensions. If you want average, get the total displacement divided by the total time. So I'm not going to, this problem is the same one. I'm just going to kind of show you all it. It's the same problem. So you're going to go 3 meters east, then you're going to go 4 meters north. We already answered. How far did you go? 5 meters. It's the same problem from before. Now it says, what's the average velocity? So this problem is just, hey, V average is my change in R over change in T. My change in R is 5. My time is 2. So, that's going to be the answer. Whatever. Good extra practice, whatever. The reason I'm skipping through this is I want to get to the ones that are actually interesting. This is fine. I really want to get to projectile motion and spend pretty much the vast majority of our time on that today, because that is, that's putting all the pieces together. All right. This one, same thing. Really, the challenge here is, can you draw what it looks like? So this one is a bird flies straight in a straight line, 45 degrees above east, a distance of 95 kilometers for 3 hours. What the x-axis due east, y-axis due north. What's the displacement? Try drawing the picture for this. That's really the challenge. If you can draw the picture, this problem's really easy. If you can't draw the picture, not so easy. So try drawing the picture, and then once you see that, you'll see the answers are like pretty straightforward and obvious. But give y'all some time. And again, on the test, I'm not going to use north, south, east, west, but I'll use up, down, left, right. Or I'll reference the x-axis, which is what referenced here. All right, so my magic arrow, 45 degrees above east, is 45 degrees above east. It's 45 degrees above that. So that's 45 degrees. And then this is going to be 95,000 meters. Great. And then it says find the x displacement and the y displacement. Oh man, a triangle. So again, these aren't super exciting. It's just, do you remember how to do vectors? Nothing really crazy. And the x component is going to be the cosine in this case because it's adjacent. The y component is going to be sine because it's the opposite. Triangles. When you all do the average velocity, it's just like that last slide, V average is going to be delta R over delta T. I already gave you delta R, it's 95,000. divide it by the time, convert it, make sure that's in seconds, and that's how you do this one. So, sure, I'll put that here, 95,000. Time is going to be 3 hours. I need to convert that to seconds, so it's going to be 3 times 60 times 60, because you got to get hours to seconds. 3 hours is a lot of seconds. So remember, whenever you're deciding whether to go up or down, just think about what makes sense. I'm converting to seconds. I need a lot of them. There's a lot of seconds in an hour. So I'm going to multiply by 60 to get to minutes, multiply by 60 to get to seconds. That's some number. 3 times 36,000. But I'm not going to try to do that in my head. That'd be silly. 10,800. And I made a tiny little mistake. See if y'all spot the mistake. It's always good when you... What did I write incorrectly? Should be 95,000, not 9,500. This will happen to you too. This is where a lot of this class is being careful. Like a lot of doing this stuff. There's a lot of steps. It's all logical steps. So it's either you do it right or you do it wrong. There's not an in-between when it comes to doing math. 2 plus 2 is always 4. 2 plus 2 is not like 4 point. It's not 5, it's not 3. And so it sounds stupid, but part of this class is just learning how to do a bunch of processes in a row and not make mistakes. It's something that's a very important skill. If you're a doctor, you're going to have lots of decisions you're going to have to make. It's going to be a stressful environment. You got to not make mistakes. And some of that is just going carefully. It's thinking about what you're doing while you're doing it. When you go on autopilot, that's when mistakes get made. Though I get it. Sometimes you're tired, and that's a whole thing. It's a challenge. It's a skill. Learning to be careful, diligent, check your stuff, all that jazz. Okay, accelerate, same thing. Nothing new here. Acceleration is change in velocity. Nothing insightful here. But I put it here just to show it. All right, great. Now we actually get to do projectile motion, and this is where things get interesting. So I'm going to remind you all, last class, there was 2 problems we did that the first one we were pretty good with. I threw something across the room, and I said, what's the acceleration up, down? And most people said negative 9.8, and that was correct, and that's awesome, and that's great. The next one is I asked, what is it in the horizontal direction? And it's 0. So when something is traveling through the air, I don't care if it's going up, down, I don't care if it's going to the side. When it's in the air, there is nothing pushing this left, right. After it leaves my hand, nothing is pushing it to the left or right. There's no rockets attached to it. There's no propellers attached to it. There's no any of that. So in every problem we do, these are called projectile motion problems. That's going to be what we're going to be solving moving forward. It's like all the 2D motion problems with projectile motion. The acceleration in the x direction is 0. That's a given. Why? Because nothing is making it speed up or slow down left, right after it leaves my hand. Yes, when it's in my hand, I'm pushing it. We are not going to do a problem where my hand is pushing it. Well, eventually we'll get to forces and we'll do stuff there. Every single problem moving forward in this slideshow is in the air. And this is a really tricky thing. It's in the air, but we're going to ignore air resistance. So it's one of those, it's really hard to describe something being not in my hand and not saying it's in the air. Like, that's just a challenge. So I'm going to say in the air, even though we're ignoring air. Just if you can find a better way of phrase, it's either it left my hand or it's in the air. That's the best terminology I could figure out for it, because I don't know. If you all think of another phrase to describe something that's flying through this without using the word air, let me know. I don't know. Anyway, we're going to say this today. It's going to be a common theme. Okay, so just to really emphasize this, gravity does not affect things left, right. You know this. You know this is true. These markers on the table are not flying to the left or right. Yes, gravity is affecting them. They are not accelerating because the table's pushing back on them, and we'll learn about forces. So that when things are in the air, that is also true. And I think one of the best examples I can give you all for that X and Y are separate from each other is that me tossing a baseball up and down like this in front of you all looks identical if I was standing on a bus going 60 miles per hour. Like, just because the bus is going 60 miles per hour, it doesn't change anything as far as this motion is concerned. If you're looking at it from the outside, you would actually see the trajectory of the ball doing this because I'd be traveling 60 miles per hour. But again, it's that independent thing. They're independent of each other. Super, super, super important. But it's a tricky thing to get your brain around. So now we're going to start getting into, okay, a little bit of vocab, things we need to know. Trajectory is the flight. I'm not going to quiz you on this vocab, but you might see these words pop up. Trajectory is the flight path. Just, if you had to draw the trajectory, that'd be that little parabolic curve. It's always a parabolic path. The time of flight is the total time it's in the air from when it leaves whatever made it move to when it hits whatever it hits. The range is the horizontal, how far it moved left, right, from where it started to where it ended. That's delta x. So delta x is the range, same thing. And maximum height is exactly what it sounds like. It's as high as it gets. Most of these are straightforward. Range is probably the only one that might be that new. I don't know. I'm going to mention them just in case. They're words you've probably heard about. They mean probably what you expect they to, but I'm just going to make it really concise and clear as much as possible. We'll see them. All right, so here's a picture. Wow, it's a projectile motion. Look, there's the trajectory. This is my max height. It blew up at the top. Great. And then this is my range, my delta x. Just, this doesn't have any math. We're not doing any math here. It's just, hey, here's a problem. This is what they're going to look like. Very exciting. Cool. Another picture. Fantastic. Okay. So, just to take a step back at why we're doing these, projectile motion problems are just like the easiest example of two-dimensional problems. There is other examples I could give. I could give like a boat is traveling and the wind is pushing it with this direction and this direction. And you can have things move in 2 dimensions otherwise. We tend to do projectile motion because they're just nice and straightforward and you're used to them and it lets you practice all the skills in a nice, consistent way. So, lots of things go through the air. Lots and lots and lots and lots of things fly through the air. So, applies to a lot of things. And it really is testing, do you understand how to do kinematics? That's the purpose of these. Do you understand motion? Basic motion, position, velocity, acceleration. These variables are going to show up in the rest of class. Like, there's less than 10 variables we're going to use in this entire class. And you've learned position, velocity, acceleration, time. You've learned 4 of them. We'll learn force, we'll learn energy, momentum, and then there's like the angular ones. But there's really not that many. You've basically learned half the variables in this class, and we're just going to use them again and again and again and again. All right, great. Split everything in X and Y. Super, super important. This next one, we're going to do a couple practice problems, top hat questions to test if this makes sense. You need to determine what limits the time. And I'll talk about this in a second. In every single problem, even if it doesn't say find the time, find the time. You're going to need the time. Just take that as a thing you're going to have to find. Even if the problem doesn't tell you to, you're going to need to. You'll see why in a second. I'll prove it to you as we're solving things. But we have to figure out how to solve the time. Remember, we're going to split things into X and Y, and then we're going to work with one at a time. Either we'll work in the X or we'll work in the Y. And then we'll go to the other one after that. We'll work in the X or the Y to find time, and then we'll do what we need to do after that. You have to decide what limits the time. And there's only 2 scenarios. If it hits the ground, it's the Y that determines the time. If I toss this baseball, when it stops is determined by when it hits the ground. It doesn't matter how far it goes left, right. Its ending path is when it hits the ground. If instead I toss this baseball at the wall, I don't care where the ground is. It's not going to stop when it hits the ground. It's going to stop when it hits the wall. So you have to make a judgment call. What determines the X or Y? We're going to see 2 examples. And then you work in that dimension. If it's the vertical, work in the vertical. If it's the horizontal, work in the horizontal. Here's an example. A dart's tossed at a dartboard across the room. What component determines the time? Is it the X? Is it after it's traveled a certain distance? horizontally? Is that what determines its flight time? Or is it after it's traveled a certain distance vertically? Is that what determines its flight time? Or neither? Whatever that might be. There's only one right answer. And to clarify, the dart does hit the dartboard. It makes it to the dartboard. All right, we'll go like 20 more seconds here. Go with what you think. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so let's just draw a picture of this. Here's a dart. I'm going to draw everything like a circle because circles are great. That's going to be a really common theme in this class. You know, the whole joke, spherical cow, all that good stuff. There it is. All right, here's a wall. What determines when my thing stops? It's when it travels this distance. Let's just pretend like it's 5 meters. Once my object has traveled 5 meters, it's stopping. I don't care how much up or down it went, assuming you threw it fast enough to hit the wall, which is why I mentioned it does hit the wall. Once it's traveled 5 meters, it's stopping. That determines the flight time. Doesn't matter how much up or down it goes. Once its X position is there, it's done. So we're going to work in our X coordinate system. We're going to work in X to determine that time. Great. A cannon shoots Joe Schmo through the air, after which he lands in a nice comfy net on the ground. Which component determines the time in this one? If these questions sound silly and obvious, fantastic, because they're really important. If they don't, I'm glad I'm asking them. I'm happy either way. All right, we'll go like 20 more seconds. All right, and we'll close it out in 5, 4, 1. All right, let's draw a picture of this one. We're on the ground. They get shot up into the air. What determines when they're done? When they return back to the ground. And let's think about this in terms of variables. My y, where do you all want 0 to be height-wise? Where do you want that to be on this picture? Up in the air, somewhere else? Where do you all want 0 to be? You get to decide. How exciting. At the ground. That is generally the rule of thumb. Generally, we'll say the ground is 0. You could technically decide it's anywhere. I don't really care. You could make the ground negative 10 meters. You may be like, why would I do that? You can. It's completely fine. Where do they end up at? What's their final y position then by that same logic? So when their y final becomes 0 again, they're done. It's no longer traveling through the air. So what determines it? The y. I have no clue how far this thing's going to go. Yes, I can decide that my initial X position is 0. I have no idea how far this is going to go. It could go any distance. That is not what limits the flight. It's when it returns back to the ground. I don't care how far it went left, right. I just care, hey, when it hits the ground, I'm done. So that's the decision making here. Really, really important. It sounds really simple. Maybe not. I don't know. But it's super important. And you're going to see when we solve problems, these are like, yeah, we're going to see that being the case. So, this whole XY independence thing is the trickiest part. I mean, it is the only thing here, and it is tricky because when you all see objects tossing, when I toss this baseball, you cannot see its X and Y components. You can't see a bunch of little arrows showing how fast it's going to the right or the left. You cannot see any arrows seeing how fast it's going up, down. You just see the baseball moving. You just see its velocity. It's going up to the right, then it's, doing this whole thing. So I think this picture helps give a sense of what's going on. This is why this idea is not going to maybe be as intuitive feeling as you might want it to be. You can't see arrows on things. All you can see is, at best, at this point it's moving up to the right. At this point it's moving less up. At this point it's moving horizontal. Like, you all have seen that. But this picture, I think, does a good job when you draw a bunch of right triangles. This entire picture is a right triangle over time. So I'm going to do the X component in red, and I'm going to do the Y component in green. The X component is the same every single time for velocity. It's not getting faster or slower in the X direction. If you shoot that thing and it has an initial X velocity of 10 meters per second, its X velocity here, 10 meters per second. X velocity here, at the highest point, 10 meters per second. Every single spot, 10 meters per second. Nothing is pushing it left or right. Now, if we look at the Y velocity, that arrow is getting smaller and smaller until eventually, at the highest point, it's 0. Just like when we toss the ball straight up, what's its velocity at the highest point? 0. And then on the way down, let's just say this is 8 meters per second. At this point, maybe it's like 4 meters per second. At the highest point, it's 0. Now it's -4, and now it's going to be -8 again. The Y velocity changes, and that's what makes the whole thing's velocity change. The X is constant, though. The X is going the same the entire time. And this idea, if it doesn't make sense to you now, it's just going to take practicing and working with it. Another way to kind of prove this is if I'm walking. So I'm walking with my baseball, and I'm walking at, I don't know, like 2 meters a second, something like that. If I drop this baseball, it doesn't just plummet straight to the ground. It doesn't, just because I dropped it, it doesn't just like as if it hit a wall. It keeps moving with me. So the baseball actually, when I let go of it, it still keeps moving with me. And in fact, if you can test this for yourself, when you're walking, just toss something straight up in the air, and you don't even have to look, and you'll catch it. If you don't even move your hand, it's a little funky because I have to do it perfectly. So I'm not looking where I'm not moving my hand at all. It keeps moving with me because its X velocity is independent. If it's moving 2 meters per second, when I toss it straight up, it's still moving 2 meters per second horizontally. Test that for yourself. Walk around, toss something straight up. Even if you have to do a really good job of tossing it straight up. If you do any angle to it, it's going to outrun you. If you do an angle backwards, it's going to go slightly backwards. But yeah, you can test this for yourself. And again, it's kind of annoying because you're used to having to catch things. Anyway, that's another great way to prove this. Walk around, toss something straight up. Don't watch it. It will return right back to your hand because it's going to keep trucking along. Anyway. All right. Done my best to try to convince you. Even if I haven't convinced you, hopefully at least we can solve some problems. An airplane flies horizontally with a speed of 500 kilometers per hour at a height of 800 meters. And it drops at greatest supplies. See the following figure. There is a figure in the problem set, but I purposely deleted it here because that's the first thing I want you to do is draw this. If the parachute fails to open, i.e. ignore air resistance, always ignore air resistance. How far in front of the release point does the crate hit the ground? It's going to keep trucking. When they release that crate, it doesn't just like as if they hit a brick wall and just plummet straight down and not move anywhere. It's going to keep moving with the plane. So anywho, draw a picture of this. If you can't draw a picture of it, you can't understand what's going to happen. It's going to be really hard to solve the problem if you can't visualize what's going on here. And a picture is a visualization of what's going on. And pro tip, start with either the ground or the plane. There's the ground. So you got the ground. The next logical thing is to draw the plane. Again, we're not looking for like a beautiful picture. A blob is fine. Everything's going to be a blob. It's great. You just need to have a sense of what's going on. Okay? It says it's flying horizontally. So this is where, again, if you don't understand the picture, it's not going to make sense. If you draw that arrow up to the right, it's not going to be correct. It is flying horizontally. All right. Great. When I'm drawing these pictures, I like to put my variables on it as I'm doing it. It helps me organize the information in a meaningful way. What variable is that going to go with? How fast it's going? Velocity. Fantastic. Velocity in the beginning or the end? It's the beginning of the problem. So 500 kilometers per hour, we are going to convert that. That's not in base units. You know what? We'll just do it now. It's going to be 500 times 1,000 to convert it to meters. And then I'm going to convert it to seconds. And how do I do that? I divide it by 60 times 60. 60 minutes in a sec, 60 minutes in an hour, 60 seconds in a minute. Great. It's 100 something based on my memory of doing this previously. 138.89 meters per second. Great. Done. Now I don't have to deal with that again. And it's 800 meters at a height of 800 meters. We have to decide, where do you all want 0 to be? Where do you all want 0 y to be? Where do you want y to equal 0? At the ground. What a great idea. So we're going to decide that the ground is 0. That's our 0. Remember, you have to decide a reference. You have to decide. So that means it's 800 meters above that. So this is 800 meters. And again, notice here I didn't put y initial or y final. I just said, hey, that's 0. Y equals 0. That's my 0 point. You know, while we're deciding this, where do y'all want x equals 0 to be? Make a decision. There's no wrong answers here. Where the plane is. Great. We'll call this x equals 0. It's not the initial. It's not the final yet. We're just saying we have to decide a reference. If you don't have a place you're referencing, if you don't decide where 0 is, you are going to decide where 0 is. It's whether or not you're doing it intentionally or not. We're being intentional. Okay. Fantastic. There's my picture. Drops a crate of supplies. And then something that might be helpful is to know that, oh, it's going to make some kind of parabolic path and end up down at the ground. Like you've seen things drop. You know how things are going to behave. Again, it's not going to literally just like pile drive straight down. It's going to keep moving just like when I dropped the baseball. It's going to keep moving the same velocity as the plane is. It just also falls at the same time. Okay. For step 1, we're going to write our givens. And what I've seen a lot of students do that I think is a great idea, and so it's how I'm going to do it this semester. When you write your x and y, I recommend making a table. So we're going to make a table with our x variables in one column and our y variables in another column to keep them separated. So we'll have our initial position. We'll have our final position. I don't know if I gave myself enough room. Through the power of copying, I can move it over though. You're just going to make a big old list of the variables, and they're separated. This really does a great job of organizing our information. We have our initial velocity, we have our final velocity, and we have our acceleration. That's all the variables. There is time, but time is the one variable that both share in common. So we don't put it in this table, but you could put it somewhere if you want. You could just put time somewhere if you really wanted to. Okay. I want you all to try to fill in this table. And I will tell you that there are only 2 boxes. By the time you fill this entire table, like just right now with just what's in this problem, you can fill in every part of this table except 2 boxes. So there's 8 givens in this problem. See if you can figure out all 8. That's the challenge to these, honestly. If you can do this step 1, the rest is cake. And then givens, identify what you're solving for. Give you like 1 or 2 more minutes to try this out, and then I'll start filling it in. Don't worry if you didn't get them all by the time I started. Just one of the downsides of lecture. I have to like cram things in. The highlighted things I just did are the only 2 you don't know. Everything else you can put a number for. All right, let's start trying it out. So what's my initial horizontal position? Where am I located left, right in the beginning? 0. We made that decision. We said where we start is 0. That's a good decision in general, is to pick either where you start or where you end is 0. Just makes the math kind of nice. Where do I initially start in the y direction? Nice, 800. Because I start above the ground. All right, moving down the list. We do not know where we're going to end up horizontally. That's actually what we're solving for. How far did we go? If we started 0, how far did we travel from 0? We don't know that. Where do we end up in the y direction? 0. Very nice. What's my x velocity in the beginning? It is 138.89. And this is the one that I had to make it wide for so it could all fit. What's my velocity initial in the y direction? Am I moving up or down at all in the beginning? Nope. So what's the value for that? 0. Fantastic. What's my and actually I'm going to skip this next. We'll do it. What's my final x velocity? It's 138.89. And the answer for why this comes in the next one. Is there anything making this thing move left or right? Anything speeding up or slowing it down left, right? Any rockets attached to this box? Zipping along? Yeah. What's my acceleration in the x direction? 0. What's my acceleration in the y direction? There we go. And these should be meters per second squared. Now, a really tempting thing is to say when it hits the ground, the velocity is 0. Because we're so used to, yes, when things hit the ground, they stop moving. That is its own problem. When things hit the ground is its own problem entirely, because then the ground is pushing on it. And you know what? Is it going to bounce? Is it going to roll? Is it going to just like plummet? And like, we always consider right before it hits the ground. Always, 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 always. Never put the final velocity as 0 when it hits the ground. It'll never be 0, because if it was 0, then how the heck did it get to the ground? If it's 0, like, okay, there is a single case where it's 0. When in an object's path is its velocity 0? At the very top. It's the complete opposite. It's not the bottom, it's at the very top when it's 0. The only time, and that's only if it's completely vertical. Oh, yeah, it's only the y component. Anywho. Great. We did it. Now you got to make a judgment. Remember, okay, so what are we going to solve for? We are solving for delta x. How far did it go? Well, delta x equals xf minus x naught. Remember, x naught, we chose x naught to be 0, so that makes my life nice and easy. It basically means, hey, find xf. What's my final position? This is why we choose the initial position to be 0. Makes it a little bit easier to solve. You could have picked any number you want, though, and it would have worked out fine. Because we're solving for delta x, really. Okay, so this is where I told you all, you have to decide what limits the time. Is it after it travels a certain distance, it hits a wall and stops? Or is it after it travels a certain vertical distance, it stops? You tell me. Great. We're going to work in the y to find time. Did the problem say find time? No. But there is no way we can figure out how far it went unless we know how long it traveled for. It's like me telling you, hey, I drove my car 60 miles per hour. How far did I go? The question is, how long did you drive for? You have to know the time. You cannot tell how far something went unless you know how long it traveled for. That's always going to be true. So you have to find time. So to do that, remember I told you all 2D kinematics problem is just two 1D kinematics problems. Pretend like this entire column doesn't exist. We are just going to work in the y direction right now and find time. It's a good old normal kinematics problem. I've got my givens. So pretend like this doesn't exist. Who cares about the x direction right now? I have got my initial y position, my final y position, my initial velocity, my acceleration. I'm solving for time. Find the kinematics equation that does that for you. Search through the list. If you haven't printed it or saved it somewhere or whatever, you will end up memorizing these equations, not because you want to, but just because you'll do enough practice with them. But you'll have them as well on the test. Oh, and if you want to move ahead, the answers are down here. The time's going to be 12.8 seconds. The distance is closer to 1775. All right, so if you look through the list and you say, hey, based on what I have, how do I find time? There's an equation that does it in one shot. But again, there's always multiple paths here. So you could do y of t equals y initial plus v initial yt plus 1/2 a. I want the time. Yay, it's got time. And I've got everything. I've got the final y, the initial y velocity, the acceleration. Fantastic. That's one option. The other option is you could say, I want to find the final y velocity using this equation. Vf squared equals v naught squared plus 2a delta y. You could find the final y velocity, and then you could do Vf equals v naught plus at. That also works. We are going to find that this method is really nice when your initial velocity isn't 0. This problem is, you'll see why that's nice in the next problem we do. We're actually only solving 2 problems today. I'm going slow and steady, making certain all the steps make sense. So I'm going to solve this problem today, and then we'll solve this one. Where is it? All right, this one. And then the other ones, I'll post the third one, I'll post the worked out solution. These problems have a lot of steps, y'all. There's a lot of chances to make a mistake somewhere. There's a lot of chances to mix up a plus and minus sign, all that good stuff. But they're very straightforward. Like, they're very much givens missing. Like, there's a very recipe way of doing these. And when you practice them enough, it'll make way more sense. So anywho, we're going to do this first method. So my final y position is 0 equals my initial y position plus my initial y velocity times time plus 1/2 times negative 9.8 times time squared. If my initial y velocity was not 0, we end up with a quadratic. And guess how, and if that might ring it. How do we solve quadratic equations if this wasn't 0? Say I had, let's just pretend there was a number here. I'm going to erase it and make it. What would you have to use to solve this? It's, quadratic formula. Negative b plus or minus square root of b squared minus 4ac over 2a. Yeah, that's going to come up in the next problem. The next problem that we do, the quadratic formula is an option, or you can break it into two pieces and do the bottom one. So maybe like, why would I do two equations? To avoid having to use the quadratic formula. That's why. So anyhow, this one you're spared. The next one you won't be. All right, so, you subtract the 800 over equals negative 4.9 t squared. T is going to equal the square root of 800 divided by 4.9. And that will come out too. I'll plug it in my calculator just to be extra thorough. 12.7775. Sure. We'll go the extra digit. Great, that's time. Okay. I want you all to think about I told you need to find time. I want you now to think about why the heck did we need to find time? That's not what the problem was asking for, but you do need it. So think about it. What the heck? What was the whole point of, what are we even doing in this problem? Remind yourself of that. And then see if you can do it. All right, so it can be, again, in these problems, when there's these steps, you can lose track of what you're solving for, and that's why we write down what we're solving for. Remember, our original goal was figuring out where the heck I ended up horizontally. Great, I figured out the time. What does that mean? It means I now can go to the x direction. I can ignore the y variables, pretend like they don't exist. And now we're just going to look in the x, and I know my initial position, I know my velocity, I know my acceleration, and I know my time. Time is the only variable that gets to go across x and y, because everything exists in the same time. So, go ahead and try to solve for it. Solve for x. Given time, initial velocity, initial position, final velocity if you really want, acceleration. Solve for where you end up horizontally. So again, we're just going to choose the equation that has what we have and has what we need. And fun fact, it's the exact same equation I already wrote. I'm just going to replace everything with x's. So V final position equals initial position plus initial velocity times time plus a times time squared. But what's really nice here is what's my acceleration in the x? 0. Who cares about that term? It goes away. In the x direction, it's super easy. The x direction is so easy. It's literally just the distance equals velocity times time. If I told you I was driving 60 miles per hour for 3 hours, how far did I go? It's just 60 times 3. And the x direction, because there's no acceleration, it's just position equals velocity times time. It's great. Nice and straightforward. Super easy. I'll do this one in green just to keep them separated. So my final position is just going to equal my initial position plus how fast I'm going. It's a constant. So if I'm constantly going this much and I travel for this long, you just multiply them. The definition of velocity is how many meters you go every second. After 1 second, they're going to travel 138.89 meters. After another second, another 138.89. After another second, so on and so forth. How many seconds have passed? Well, we found that. And that's it. You plug that into your calculator, and it's going to tell you how far you went horizontally. Horizontally, it didn't get faster or slower. It just kept going until eventually it hit the ground, causing it to stop. What happened after it hit the ground? Don't care. Don't care if that box exploded, rolled, jumped, whatever. That's not the problem. That's really complex. That's a problem NASA has to figure out whenever they're landing on a planet. How are we going to land? Are we going to land gently? Some of the recent ones was literally just put a bunch of I don't exactly know what they put around it. I don't know if it was air cushions or what. Put a bunch of cushiony stuff around it, just have it bounce on the surface. Saves them a lot of money compared to other things, and it's a lot more foolproof. They have to make this decision. You don't. That is a whole complex problem in and of itself. I'm just asking you the basics right before it hits the ground. Let's just worry about one part of the problem at a time. There you go. Projectile motion. This is a good, and this is the simplest example I can give you on this. And that's not to intimidate you. That's not to be like, oh, it's going to get terribly worse. It's just to let you know we're going to add a little bit of bits and pieces to it. So the next example is going to add one additional element to it. And that additional element is going to be, we're going to now, instead of having a horizontal initial velocity, we'll have a angled initial velocity. So these problems, again, kind of build. And there's really only so many variations on these. Something I want to point out, because you all might stumble upon these, and I don't really like these equations. They are useful, but you can only use them for one specific scenario. So these equations, they're shortcut equations that basically give you how far. This equation here tells you how far you traveled if you know the initial velocity and the angle. It only works if you start and end on the ground, if you start and end at the same height. This equation tells you how far you travel only if you start and end at the same height. The problem I'm just about to give you, this doesn't work for. This equation tells you how high you're going to go. This one always works. That's fine. And the time of flight tells you how long you're in the air only if you start and stop at the same height. Only if you start and stop at the same height. This would not have worked for the problem that we just solved. Okay? Because we didn't start and stop at the same height. So these equations can be useful, but you have to know when they're appropriate to use, which is equations that start and end at the same height is a better phrase than what I just put than on the ground. Start and end at the same height. If you try to use these equations with anything else, it will give you the wrong, with the exception of the middle one, it will give you the wrong answer. So, all right. This problem is kind of in your problem set. I just varied it. So in the problem set, the only thing I changed was I made it so that we're on a cliff and it's kicked at an angle. So if you're trying to look in the problem set and you find a problem, you're like, why isn't this identical? All I've changed here. An astronaut on Mars kicks a soccer ball at an angle of 30 degrees and you start on a cliff. If the acceleration of gravity on Mars is 3.7 meters per second squared, what's the range of the soccer kick if it lands at the bottom? What would be the same range if it was on the moon? Draw a picture. If you can't draw a picture of this, you can't solve. You can, maybe. It's going to be really hard to do. I don't know. I can't imagine. Solving a physics problem without having a sense of what's going on just feels unpleasant. So I'll give you all a moment for that, and then I will just work through this one for the rest of class for the sake of time. You can start trying to do the givens as well if you want. You can go through all the steps. You don't need to wait on me. All right, so we're at cliff. There it is. There's my cliff. There's my ball. And it gets kicked at an angle of 30 degrees. If it doesn't specify otherwise, we're going to assume that's 30 degrees up. It says positive 30 degrees. If it said 30 degrees below the x-axis or negative 30 degrees, then it would be downwards. And there's nothing preventing you from kicking the ball downwards. Like, you're allowed to do that. That is a possible problem. And it does change things. But in this case, it's a positive 30. So at 30 degrees, 15 meters per second. Meters per second, what variable does that go with? Velocity. Initial or final? Initial. These are the kind of questions you want to ask yourself to make sure you're labeling it correctly. The better you can label your variables, the easier your life's going to be. Now, hopefully, one of the things that should immediately trigger in your mind is I'm going to have to draw a triangle. We have to break that into X and Y. Like, that's just immediately, we're going to have to, let's just do it now. We know we're going to have to split things into X and Y. Let's do it sooner than later. We cannot work with this variable as is. We can only work with them when they're in X, Y. So, triangle. When you draw this triangle, not only do you need to draw both sides, you need to draw them as arrows. So, this velocity, is it to the right or to the left? So we make the bottom one to the right. Is it up or down? Perfect. Okay. Now we're going to label these two sides. They are both velocity. Anytime you draw a triangle, they're all the same variable. If it's a triangle for velocity, it's all velocity. If it's a triangle for acceleration, it's all acceleration. If it's a triangle for position, it's all position. Do not put a velocity and a position in the same triangle. It's apple and oranges. You can't do that. All right, great. They're both velocity. They're also both initial velocity. Same thing. It's all the same variable. And then you just got to say, this one's my X, this one's my Y. And we're going to have to find them. Let's just do it now. It's a triangle. We got this hypotenuse and the angle. We're going to find the Y component. I'm just going to tell you, and I'm going to let you. This is going to be sine because it's the opposite side. Not because the Y component's always sine. It's because it's the opposite side. My X component is the adjacent side. And then we just plug these on in. I'm the kind of person that I've learned if I don't do something immediately, I might forget to do it later. So that's why I mentioned doing it now. Everyone's different, but I've just found that's how my brain works. And we have to make a judgment call in each of these cases. When you do this math, it will not tell you whether it's positive or negative. So you all tell me, is this Y velocity positive or negative? Is it up or down? Positive because it's up. If it was down, you'd have to put a negative sign. The math's not going to do that for you. You have to make that decision. X component, right or left? Right, so that one's going to be positive. Also, while I'm doing this, remember there's little checks you can do in your head that make it less likely for you to make a mistake. This thing's 30 degrees. 30 degrees is more horizontal than vertical. My X component should be bigger than my Y component because 30 degrees is more flat than steep. Little checks like this are good things to keep in mind. The more you can think about these things, the less likely you are to make a mistake. All right, fantastic. Before I start labeling the rest of these things, where do you all want the initial X position to be? Or sorry, where do you want 0 to be in the X direction? Where do we want to define X equals 0? Where the ball starts. Great idea. That's X equals 0. Where do you all want Y equals 0 to be? At the ground. Great decision. That works for me. Doesn't matter if you all decided to make the ball start at Y equals 0. That's fine. If you did that, then its final position would be negative 30. If you go down, your position should get smaller. So, anyway. Great. I think that's everything one more thing. We can say this cliff is 30 meters tall. Great. We're going to do the exact same thing, y'all. Make the table. We have our X initial, we have our initial position, we have our final position, we have our initial velocity, we have our final velocity, and we have our acceleration. My lines here aren't the prettiest, but they'll get the job done. And then we just start chucking things in here. Fun fact, this problem is actually just like the last one. The two things that we're missing are XF, the final X position, and the final Y velocity. Initial x is 0 meters. Initial y is 30 meters. Final y is 30. Initial x velocity. I'm just referencing the picture. That's where I'm getting all this information from. The beauty of a good picture is it gives you everything you need and you don't have to read the problem again. 7.5 meters per second. My final x velocity is the exact same. My final y velocity, who knows? What a mystery. We are not on Earth. What is my acceleration in this problem? Yeah. So there's a subtle thing here. The acceleration the problem it lists is positive. But if you put this as positive, you're saying that gravity is making it fly up into the air. It has to have a negative sign. If you don't put that negative sign, your whole problem falls apart. Again, it's thinking through these things. It's a tiny, seems like a tiny thing, but it's going to make a big difference. And again, it's one of those that when you think, which way does gravity pull? Downwards. Even on Mars, that's true. We have to put the negative. Otherwise, we're saying that gravity is making things fly up into the air. And you'll find that mathematically. If you do this problem with 3.9, positive 3.9, you will never reach the ground. Like, you will not get a positive time. You'll find a time that's negative, which means you have to go backwards in time to reach the ground, which is not the case. Thanks. Good catch. Yeah, no, that's good. If I'd used 3.9, we would have gotten the wrong answer. It will happen to you. All these little things. One thing I want to note here, I will not give a problem this involved as a multiple choice problem. There's so many steps involved in this. If it was multiple choice, it would be kind of mean, because if you messed up any one of these steps, you're not going to get the right answer. This problem would be an example of a free response problem, where there's multiple steps involved, but you're graded on partial credit. So if you make a tiny mistake here and there, you accidentally put a positive instead of a negative or whatever, you'll get most of the points. You'll get 80 to 90% of the points if you make small errors. If you show that you know what you're doing, you'll get most of the points. Now, on the test, what I could do is give you this problem and say, what's the initial x velocity? That's something I could put as a multiple choice problem, because that's just a piece of this. Or I could say, what's the initial y velocity? Or I could even ask you, what's the final x velocity? It's a given. It's not, you don't have to do, the only math is just, there's two things you'd have to remember there. Hey, I need to find the x velocity here, and then I need to know that doesn't change. That's a really common problem for me to ask is, hey, a ball gets launched. What's its x velocity 10 seconds into the air? Makes it sound way more complicated than it is. It's just the initial x velocity. It's testing if you know that the x velocity is constant. So, be prepared. I think that's one of the questions on the quiz. I really like doing that. Great. We're solving for XF, just like we're solving for how far it goes. Well, my initial position we decided was 0. So it's, just, hey, what's my final X? Okay. For the sake of time, again, the beautiful thing is once you all build this, once you all do steps 1, 2, 3, you don't have to read the problem anymore. That's why I never copy it. After I do that, I don't worry about the problem because I don't need to read it anymore. If I've done a good job of collecting everything I need, great. I'm good to go. I cannot have to read those words. We have translated the problem to math. So step 3, we got to make a judgment call. What limits the time? We're going to have to, it didn't tell us to find time. We're going to find time. What limits it? X or Y? Is it when it hits a wall or is it when it travels a certain horizontal distance it stops? Or is it when it travels a certain vertical distance it stops? Vertical distance. So like before, ignore the X. We don't care about it right now. We're going to find the time by using the Y components. How are we going to do that? The exact same way again, we got choices here. So this is where I warned you all this is going to come up. We can use the exact same equation we did in the last problem. Y final equals Y initial plus V initial t plus 1/2 AT squared. Sure. Let's try it out and see what happens. I've already warned you all the consequence of it. It's not bad. It's not the worst thing in the world. My Y final is 0 equals 30 plus 7.5 t plus 1/2 times negative 3.7 t squared. It's a quadratic. You got to do the quadratic formula. It is what it is. If you solve it this way. Totally works. You could totally do the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't remember how to do the quadratic formula, it's a good exercise to remind yourself. Unfortunately, there's physics problems. You just got to do the quadratic formula. Like, it exists for a reason. It exists because that is the only way to solve these problems. Unless you have like a graphing calculator that can give you the intercepts or do it for you. I don't really care. I don't really care if you whatever. Great. That's one option. The option I tend to go for instead, because I've just made too many mistakes plugging in numbers in the wrong spot here. It's so easy to accidentally put the wrong number, forget to square it, or forget to put the minus sign. I do want to note there's two answers here, plus or minus. Which one's going to be correct is going to be the one that makes sense. You may be like, that sounds stupid. You're going to get a positive time and a negative time. The correct answer is the positive time. Negative time means you went backwards in time. So we're not going to go backwards in time. Okay. Alternatively, you can do VFY squared equals V initial y squared plus 2a y final minus y initial. This will let us solve for the final y velocity. And then we can do VFY equals V initial y plus AT. Fun fact, I'm secretly doing the quadratic formula when I'm doing this. If you actually wrote it all out, this is secretly doing the quadratic formula. You can kind of see it. What's the opposite of a square? It's a square root. It kind of looks like the square root, like you can see pieces of that. So you're secretly doing the quadratic formula, but what I like is it's in pieces. When you try to plug a bunch of things at once, the more things you try to do at one time, the more likely it is you might make a mistake. It's harder to check your work. So this problem just basically is doing the quadratic formula in two pieces, which for me at least reduces my chance of mistakes. You do whatever you're the most comfortable with. We're just going to chuck this thing off somewhere. I need room. All right, so we're going to do this. So we're going to do the final, we're going to solve for the final y velocity. That's going to be V initial squared, 7.5 squared plus 2 times negative 3.7 times 0 minus 30. Don't do 30 minus 0. That's also a classic mistake. People will do the bigger number minus the smaller number. It's y final minus y initial. If you mix them up, you'll get the wrong answer. It'll happen. All right. This equals a number, 7.5 squared plus 2 times negative 3.7 times negative 30. Double checking it all went in my calculator. Great. Okay, so that's going to be 278.25. That is not my final y velocity. That is my final y velocity squared. How do you get rid of squared? Square root it. Now, there is something subtle here that a lot of people will forget. It's very, very easy to do. When you plug this into your calculator, the square root of 278.25, it will spit out a positive number. Think about what a positive velocity means. Is a positive velocity up or down? Up. When my thing hits the ground, is it traveling up? Nope. So what's up with that? Remember, whenever you do a square root, there's a plus and minus secretly in front of it. Anytime the solution to the square root of 100, negative 10 squared is 100. Negative 8 squared is 64. You have to make a judgment call. Which one's right? The negative one. So you do the square root of this, and you will get, again, you plug this in your calculator, you're going to get 16.68. You have to make a judgment call that the final velocity is negative 16.68. If you do not do that, you will get it wrong. This problem is an exercise in being careful. That is the nature of this. And then last step, y'all. Very, very last step. We're basically there. We're just going to take that and put it in the equation. So I'll do that in purple or something that's legible. This one will be in blue. So negative 16.68 equals 7.5 plus negative 3.7 times t. If you subtract 7.5 and you divide by 3.7, I just don't have room, so I'll chuck that in another slide. I'll make everything small. I want to fit everything here. small. All right. So negative 16.68 minus 7.5 equals negative 3.7 times t. T equals whatever the heck that is. 24.108. Negative divided by negative 3.7 equals something. 6 points. Yeah, good. 6.54 seconds. And there you go. That's a 2D kinematics problem. That's kind of the complexity level I need you to be able to do. Yeah, it's a lot of steps, y'all. It's putting everything we learned all together. You can do this. You just have to practice them. The last thing I want to mention, this problem is really cool, but there's some tricks here. This problem, you got to know a couple things. If it takes 20 seconds to do the entire trip, how long does it take to get halfway there? Or to the highest point? T equals 10 seconds. What's its velocity at the highest? What's its vertical velocity at the highest point? 0. And then one last thing. If it launches with a vertical velocity, I don't know what the number is going to be, but let's just pretend like it's 10. I don't know what it is. How fast will its vertical velocity be at the end? If it's positive 10, if its initial y velocity is positive 10, if I toss the baseball upwards with positive 10, how fast is it when it returns back to my hand? These are the tricks you have to do to solve this problem, because I literally only give you the angle and the time, and that's it. And that's enough to actually solve this entire problem, which is kind of cool. All right. I don't know what these numbers are, so I'm just going to actually put them this way. Anyway, see y'all. If you have any questions, I'm here. Hey, what up?
How did you get the initial velocity in the y direction of 7.5 meters per second?
Here?
Yeah, like I just don't know where you got that number from.
Triangle. You know the hypotenuse, you know that. Yep.
Oh, okay, so you solved it like
Yeah.
the side and then
Yeah, I did it right over here.
Okay.
Yeah.
Okay.
Yep. No, it's a great question. Yeah, so I did it immediately because anytime you see something like that where it's an angle, I'm like, I know I have to do this. Might as well do it now.
Okay, got it. And then also for the formulas, so whenever I see v of t means velocity of time.
Velocity at some time, it's the same as VF. Same exact thing.
Okay, so then I should just look at it as xf